We now look at how to prove the theorem P less than R that we added as a guard for the event's decrements. Again, please note that we have declared guard number 2 as a theorem rather than not a theorem because we want to prove that this P less than R expression can be inferred from the existing guard and axioms and invariants from our context in machine. Let's see how we prove this. First of all, let's double click on the corresponding proof obligation that has not been discharged. The theorem of guard number 2 for decrements. Let's double click on that and we switch to the proving perspective, and this is what we are supposed to prove. This expression here is the guard of the event's decrements, and this is the new theorem that we added for event's decrements. However, this guard alone is not sufficient to prove the truth of this theorem. What we have to do instead is to search for the relevant hypothesis from the axioms and from the axiom in the context and the invariance in the current machine. That's what we are supposed to do. But before we do that, let's look at a visual intuition of how we are supposed to tackle the whole proving process. First of all, what we are supposed to prove is that P is less than R. So P over here is less than R. In other words, P is to the left of R. And let's review what we have known already as facts. First of all, we have f of R larger than V from the guard of the current event, which is decrements. We have f of R is larger than the target value V that we are searching for in the array. Secondly, we have the sorting property that we declare from the context, and it has been declared as an axiom. Basically, the sorting property says that if an index I is smaller than or equal to the other index j, then it must be the case that the elements contained in element at index I in the array F is smaller than or equal to the elements contained in index j in the same array F. So that's a sorting property. And in the invariance of the current machine, we also have this to say V is in the relational image of F from the interval of P up to Q. So we are saying that from between the interval of P and Q in the array F, the V that we are looking for must exist. So now let's think about how these two facts can actually help us. First of all, from the guard that f of R is larger than V, so f of R is larger than V, we know that also from the sorting property that everything that's to the right of index R must be even larger than the target elements V. So the element that we're looking for, which is V, cannot exist to the right of index R. And also, because of this property here, V must be somewhere in the array. If V cannot be to the right of R and index R is not the element that we are looking for, then now V must be to the left of index R. So that's the conclusion we can make, and that's exactly the thing we want to prove. We want to prove that index R must be to the left of the initial value of R, and also we do not go out of boundary of the array, which means R must be greater than P. So if we do the decrements of R down to R minus 1, this expression is still well defined. Okay, so that's basically the thinking process that we have to bear in mind while we are doing the proof. So now we'll show you how to put these two known facts as hypotheses in the Rodin platform. So let's go back to the Rodin, and we will search the hypothesis from the left panel here. So first of all, we select the sorting property, and we select the assurance that the V element that we're looking for must exist between P and Q. So we add these two hypotheses into our context, and now, because the thing we want to prove is P less than R, let's reformulate this relationship a little bit differently, but equivalently, which is R is greater than P. And if you look at the expression here, so whenever you see an implication like in this form, so you should think about using the rule of modus tollens, which means because we are looking for R greater than P eventually, so we somehow, if we are able to negate the less than or equal to relationship here by, if we actually put R less than or equal to P over here, then eventually we might be able to negate the relationship to become R greater than P, which is exactly what we are trying to prove. So that's something you have to pay attention to whenever you see some greater than or some relationship in the goal, and you have some implication in the hypothesis, then you should think about if there might be a way for you to negate the consequence and the antecedent so that you can prove that eventually. Okay, so the rule that we're going to use is called modus tollens. Let's just have a look at exactly how the modus tollens is defined. Let's go back here. So this is the rule of modus tollens in general. Given some hypothesis and some implication P implies Q, and we are trying to establish the goal G. In order to prove this here, it would be sufficient to prove two things. Because we know that by contrapositive, P implies Q is equivalent to not Q implies not P. So what we have to prove first is to prove that the hypothesis H entails the negation of the consequence. And once we have got the negation of consequence, we know that the negation of the antecedent P should follow, and we only have to prove as a remaining. What remains to be proved will be that the hypothesis, together with the negation of the antecedent, should entail the goal G. To put that into our case of the event decrements. So what we try to prove eventually will be P less than R. And from the implication that we saw in the Rodin, we actually have things we want to instantiate something like this. To say R less than or equal to P implies f of R less than or equal to f of P. And it would be sufficient to prove by the modus tollens rule that, first of all, the existing hypothesis, meaning the existing axioms and invariants, entail f of R larger than f of P. We prove that first, and then we can apply the negation of the antecedents, which is R larger than P, will entail the final goal of P less than R. As you can see, this guy here is equivalent to here. So once we have done that, it will be trivial. So the main thing to prove is this guy here. Okay, but before we get there, let's just get back to Rodin and catch up with the process. Okay, again, so we are trying to prove something, the relation we are trying to get eventually will be R greater than P, which will be the negation of this relation here. So we want to instantiate I as R, and we want to instantiate J as P. And we instantiate the universal quantifier, and now here is the point to apply the modus tollens, because we want to negate the less than or equal to relationship to become greater than. So we go over, just put your mouse over the implication sign, and now we want to apply the modus tollens. And once we do that, what we have to prove is the negation of the consequence is true. And then the second thing to prove is that given the negation of this antecedent, this goal should follow. So you actually see two things being generated from the Rodin. Okay, let's do modus tollens here, and you will actually see two things being generated. So this guy here would be the f of r larger than f of p, this is actually the negation of the consequence, and this guy here is the negation of the antecedents. And using this, we have to prove this eventually. But let's take care of the negation of the consequence first. Okay, so now we want to prove that f of r is larger than f of p. And the only way to go further would be to remove the membership. If you look at this expression here, that says V is a member of the relational image of f from the interval of p up to q. That means there exists some elements index such that f of, let's say index x, such that f of x is equal to v. That's exactly what this expression is saying, and that's what the Rodin will rewrite this expression to. So let's remove the membership, and you will actually see that there is an x such that x maps to v is in f. So if you think about, reformulate this expression a little bit, it is equivalent to f of x is equal to v. And so if you actually substitute v by f of x, you will have f of r larger than f of x. And what you really want to prove is that f of r is larger than f of p. But how do we actually proceed further? Okay, remember this, we have f of r larger than f of x. Let's just go back to our diagram to make it more understandable. So what we have is f of r is greater than f of x. What we want to prove is f of r is larger than f of p. We only need something to actually in between to derive the theorem. So we will actually use something called the transitivity of the relationship. So basically what we want to do is to add some hypothesis into the context saying f of x should be greater than or equal to f of p. So if you think about the whole logical process, we know that f of r is larger than f of x. If we also know that f of x is greater than or equal to f of p, then we can get that f of r is greater than f of p. To be more precise in words, you can see that we want to prove f of p is less than f of r, so we choose something in between. So f of x less than f of r, something we have already known, and we also add this hypothesis to say f of x is also larger than or equal to f of p. And by transitivity, we can prove this sub-theorem here. So let's go back to Rodin. And what we have to do is to say, okay, again, to prove that f of r is larger than f of p, we have to add some intermediate theorem. So we say f of x is greater than or equal to f of p. To add this as a hypothesis, AH over here. If we do that, let's see what remains to be discharged. First of all, x is in the domain of f. This is true because x maps to v is in f, which means f of x is equal to v. So x must be in the domain of f. Okay? So let's see if that will blow away. So let's try again. Good. So that blows away. So now, let's see what remains to be proved. This guy here. So first of all, we know that f of r is larger than v, and we know that x maps to v is in f. And we also, it turns out the only thing we need would be, okay, let me just isolate the theorems that we need in order to prove that. Okay, so let's look more closely on this. So f of r is larger than v, and x maps to v is in f, which means f of r is larger than f of x. And we need to add some hypothesis here. In fact, Rodin will find the relevant hypothesis sometimes for you, so you don't really have to do that, but I'll just do it for you in this case. So if we do this, we want to say V is in the range of F. If you do this, so because we are guaranteed that V is in the range of F, and X maps to F, to V is in F, and we know that X is in the range of P up to Q, so it's guaranteed that X must be greater than or equal to P because the array is also sorted. So let's click on that. Okay, it blows away. Now we want to prove that f of r is greater than f of p. So let's isolate the hypothesis that we will need to complete the proof. So we certainly need this guy here. So we do not need that. We need this. We don't need that. And we need this guy indeed because we want to specify the type of variable f, which is a function, because we are using the function application in the hypothesis and we want to make sure that expressions make sense. We do not need this guy, so let's filter out the irrelevant hypothesis. So now we have f of r greater than f of x, because you can see that x maps to v is in f. So we have f of r greater than f of x, and f of x greater than or equal to f of p. By transitivity, we will certainly get f of r greater than f of p. So hopefully this will blow away by Rodin. It does. So last but not least, remember when our intention of applying the modus tollens is because we want to make sure we want to get the negation of the antecedents such that it can be put in the hypothesis, and from there to our eventual goal it will be trivial. Okay, let's have a look how this works. We have the structure of not P or Q, and remember not P or Q is equivalent to P implies Q. So let's just rewrite this expression here by disjunction to implication. So now we have an implication here, and usually if we are pretty sure this antecedent is true, then we can directly then we have to prove it trivially, and then we can directly apply the consequence. So now we apply the modus ponens rule, and we do that, and now this is the antecedents that we just saw, which is r is in the range of 1 up to n. This is indeed the case because that's what we have declared as the invariance, and this will just blow away. And now what remains to be proved will be trivial, because as you can see here, r greater than p is equivalent to p less than r. So you've just proved that, it blows away. So now we completed the proof of the guard that we added as a theorem for the events decrements.